Okay. Let's talk about a couple of things, and then we're going to finish this set of notes, and we'll start the next one. Okay. So, couple of things. First off, you have a quiz due today. Yes? Pay attention to when it's due. You probably could answer most of the questions already, and then we'll finish the last of the things that apply to the questions today. So I just want to talk about something because I got an email this weekend from a student who was asking me for some guidance on the quiz questions. And I was a total jerk, and I did not answer her questions, but I tried to let her know why I didn't answer her questions. So do you have any idea why I wouldn't confirm or deny that she got her questions correct or tell her the answers to the quiz questions? Any idea why? Is it because I'm a bastard? What?
You have to do the work for her.
Well, I don't even mind doing the work for her, but one of the things that I want you to kind of understand about phys is that the struggle is the learning. Like the not knowing and figuring out how to know when you don't know is phys. Like that is it. And so instead what I directed her to do was I clarified just to make sure that she understood specifically what I was asking. And then even though I am an introvert and I understand why you don't want to, I encouraged her again to ask you guys, ask people, to bounce it off of someone so that you can talk through your logic, because that is better for her process than me answering her question. So what I want you to understand is that I really like a lot of the questions that I ask, and especially as we get further going, they're not rote memorization questions, they're application questions, which is really what I'm trying to foster in this class. And you kind of have to practice it. And sometimes you have to go out on a limb, but when you go out on a limb and you're able to check with someone, you can actually fix your knowledge. So I don't want you to think that I won't ever answer your questions. For instance, if the quiz closes and you still don't understand why the hell you got a question wrong, you should, again, talk to a friend. And then if you still don't get it, you should ask me. And you'll actually get more benefit out of asking me if you ask in class than via email, because then somebody else also had your question, and we can clarify it for the entire group. So I will answer your questions, but not until I've seen you sort of go through the processing of trying to answer them yourself. So, and I will. I won't leave you with a wrong impression. So you have a quiz over homeostasis. A good 25% of you guys didn't do the first quiz, so I don't want that to happen to you again. So make sure that you get it done. Even if you're not sure about it, go answer something on all of them, right? And then go back and figure it out. Okay, and you guys, we're going to finish homeostasis today, and we're going to start on metabolism today, and metabolism is what you guys are going to be doing in the lab this week. So, all right. So where we were last time is we talked about sort of this concept of, in order to maintain body-wide homeostasis, when individual cells have different jobs, what you need is communication between the cells, right? And what we said last time is the mechanism of communicating between cell A and cell B is what we call a chemical messenger. And so we're going to talk about the categories of chemical messengers today. And the rest of this set of notes, usually you've had a lot of that in other classes. Maybe not the specific examples, but certainly homeostasis and negative feedback and that kind of stuff. But I didn't learn a lot of this stuff until I actually got into physiology, like the types of chemical messengers. So what we are going to do is we're going to talk about the categories of chemical messengers today. But I want you to understand how chemical messengers are classified, so that you can start to predict what one is versus another one. The way that chemical messengers are classified is not first by their chemistry, it's first by their behavior. So for instance, some chemical messengers are dumped into the bloodstream and travel from point A to point B through the bloodstream. Those are collectively considered hormones, even if one is a lipid and one is a peptide. Doesn't matter, right? Because if you know it gets dumped into the bloodstream, you can predict something about the amount of it you might need, how quickly it was going to cause a target cell response, right? How broadly it would be able to have an impact. Does that make sense? So those are all categorized as hormones. If instead you're released within a tissue, you guys are all cells in a tissue, and you're released to communicate with your neighbors, you're what we call a paracrine agent or a paracrine factor. And again, it allows you to predict how quickly you can cause a response, whether you're likely to cause a body-wide response, those kinds of things, right? Or if you're a neurotransmitter, a neurotransmitter is released by a neuron right next to its receptor, and you can predict some things about it. So long before you categorize them by chemistry, you categorize them by how they travel to their target cell. So what we're going to do is that first. So let's start predicting how you travel to a target cell. So remember what we defined as a target cell last time was any cell with a receptor for that chemical messenger. Good? So let's talk about the categories of chemical messengers. So the functional classes of chemical messengers, they all end up going into the extracellular fluid, meaning they don't stay in the intracellular fluid. And then they all travel from point A to point B, from the cell that releases them to the target cell. So they're all going to have that in common. But categorization goes like this. So first, we have hormones. So what makes something a hormone? A lot of times before people take biology in college, they are under the impression that hormones are all related to sex and reproduction, right? Because that's the context a lot of times that you refer to the word hormone. But of course, you guys know that that's not what makes it a hormone. Some hormones are related to sex and reproduction, but an awful lot of them are not. As a matter of fact, most of them are not. So what makes it a hormone is that it is secreted by any organ or any cell. You call them endocrine organs, but note to self, they're not always glands. Any cell secretes it, it gets picked up by the bloodstream, and that is how it travels from point A to point B. It travels through its target cell, travels to its target cell through the bloodstream. That's what makes it a hormone. So this allows for what we call endocrine communication. So I want to start predicting some things about endocrine communication, like what do hormones have in common? So first thing is the target cell response going to be instantaneous, like within nanoseconds? No, it can't be, right? You have to dump into the bloodstream, you have to circulate it, right? So we can think about estrogen, right? Estrogen is released from the ovaries, but it's got target cells all over the body, right? Okay. And the response to estrogen is slower. How slow? Estrogen is hours to days, but insulin is minutes to hours, right? It depends on a few things, and we'll talk about that. But either way, it's not instantaneous, right? So if you looked at, for instance, a diagram of the target cell response over time, what you would see with a hormone is it would take a little while to get to maximum target cell response, right? Okay. And does it immediately turn off the target cell response when you stop secreting the hormone? No, conceptually and logically, if it's still circulating in the bloodstream, then you're still going to have response, right? So you're going to have a relatively slow upsweep. You're going to hit the maximum. You're going to have a relatively slow downsweep, right? Because in order to stop responding to the hormone, you have to get it out of the bloodstream. Generally speaking, you have to break it down. Sometimes that's a liver or a kidney thing. Sometimes it's a target cell thing. Does that make sense? So slow upsweep, slow downsweep. How about the number of places or the number of target cells or the likelihood of widespread responses? Is a hormone a chemical messenger that could have widespread responses? Is there any limit to the number of target cells that you could interact with? Not really, because you go through the bloodstream, right? So for instance, estrogen, right, of course affects the reproductive organs, it affects the breast, it affects fat, right? It affects hair growth, it affects the brain, right? So there's really no limit. So hormones can have widespread effects on the body. Again, back to insulin. How many cells in the body does insulin impact? Most of them, right? It's not all of them. They don't all have insulin receptors, but most of them do. Okay, so relatively slow upsweep, relatively slow downsweep can produce widespread effects because it travels through the blood. And then hormones, what do you think? Hormones are more likely to be used for what? Intrinsic control or extrinsic control? Yeah, generally speaking, that is one of the ways that you have a problem that you can't handle and you call in the troops, right, is that you involve the endocrine system to actually calm the troops. Is that okay? Now, let's just predict a little bit about the level of hormone you need to release. So, if, for instance, I released insulin from the pancreas and it has to go to most cells in the body, do you think, compared to like a paracrine agent that communicates with its neighbors, you need to release more or less hormone? More, because even if I release it and it goes into the bloodstream, is it really like having a direct missile targeted impact on the target cell, or is it basically just dumping into the bloodstream and working with statistics, right? So a lot of times you have to overdo it on the amount of hormone you release. Does that make sense? Okay. You have to release more than you would actually need if, for instance, everyone found their target cell, because you're just dumping it into the bloodstream, right? It's just going to the bloodstream. Does that make sense to you guys? Okay, so as far as quantities, with hormones, quite often you have to overdo it based on even the number of target cells. Okay, so some examples of hormones, and of course we spend an entire section in this class on hormones. You will learn 32, 35 different hormones. I can't remember exactly how many. But again, hormones, some of them are sex hormones like estrogen and testosterone, but there's also thyroid hormone, which is a metabolic hormone, and insulin and glucagon, which are related to regulating sugar and nutrients. There are tons of hormones, and we will learn a lot of them, and you will remember a lot of them. Okay, one other little category that your textbook talks about, and some other textbooks too. This is still a hormone, but I don't know why they think it needs a special name, because I don't. And they call these neurohormones, and a neurohormone is simply something that is released by, imagine this first cell right here is a neuron, but it gets dumped into the bloodstream to travel to its target cell, right? Isn't it still behaving like other hormones behave? Yeah? Okay. So for me, I just lump them in with hormones. I don't care what released them, because that's not the difference in physiology, right? The difference in physiology is collectively how they travel and how they impact their target cell. But there are two that are classically considered neurohormones released by neurons to act on different target tissues. Oxytocin is one of them. It's released by neurons from hypothalamus to posterior pituitary, dumped into the bloodstream to target the uterus, among other things. And then ADH, which is antidiuretic hormone, we'll learn about later. It's released from the same general location, and it targets the kidneys and the blood vessels, but still they're hormones. They just get dumped in. So note to self, when you run into the word neurohormone, realize that it's a hormone, okay? And I'm going to lump it in with the hormones, okay? All right, so, and it is different, and the reason I don't use it really is because I don't want you to confuse it or think it has more in common with neurotransmitters than hormones, because it doesn't. Here is a neurotransmitter. So in order to be a neurotransmitter, you have to meet two criteria. The first one is that it has to be released by a neuron. And the second one is that it has to be released right next to its receptor. Do you see? Right next to the receptor. Like microscopically separated from the receptor. Okay, that makes sense? So this allows for what we call synaptic communication. And synaptic communication is generally another type of extrinsic control. And synaptic communication allows for neurons to communicate with other cells. Neurons, quite often, like in your cerebral cortex, are communicating with other neurons. Okay? But neurons can, for instance, like the neuron that is communicating with the skeletal muscle fibers in my little toe, its cell body is all the way up here in the lumbar region of my spinal cord, right? And it's communicating with my little toe all the way down here. Does that make sense? Because the axon is that long, okay? So synaptic communication. Now, what do you imagine? Is neurotransmitter communication going to be faster or slower than endocrine? Faster, okay? It's faster because you release it right next to the receptor. It's also faster because transmission of the impulse down the axon is up to 250 miles an hour. Really fast transmission down an axon. Way faster than circulation, for instance, right? So almost instantaneously. How about targeted or broad effects? What do you think? Targeted. You release it right next to the receptor, and then, by the way, you actually immediately pull it out of the synapse so it doesn't cause a response without you telling it to. Release it at the target. So it is not going to, for instance, have broad effects typically. It's going to have really targeted, quick on, quick off, right? Turn it on, turn it off, turn it on, turn it off effects. That's what's going to make it a neurotransmitter. So the communication is faster, but it's shorter lived than endocrine communication. How about how many neurotransmitters you need to release? Higher concentration, lower concentration than hormones? Way lower concentration, right? You release far less neurotransmitters than you actually do hormones, right? Because they're right next to the thing that they're actually trying to talk to. Does that make sense to you? Okay. Neurotransmitters, by definition, do not go into the bloodstream, okay? And if they did, if it was released from a neuron and it went into the bloodstream, it would be a hormone/neurohormone, right? And then it would behave far more like a hormone than it would like a neurotransmitter, right? So the physiology would be very different once it went into the bloodstream. Everybody okay with that? Okay, so neurotransmitters is my favorite part of physiology. We don't do it yet, but we'll do it later. We do a whole section on neurotransmitters, and neurotransmitters are super fascinating to me. So neurotransmitters can either communicate between neurons, of course, or they could communicate between neurons. And do you remember any of the other things that neurons can boss around? What other kinds of cells can neurons tell what to do?
Muscle.
Yeah, muscle, all three types, right? And glands, okay? So there's a whole bunch of neurotransmitters. We learned 20-ish neurotransmitters. Dopamine, serotonin, acetylcholine. They're fascinating. The ones, interestingly, that we know the most about are the PNS neurotransmitters. And any idea why we know more about the PNS neurotransmitters than the CNS neurotransmitters? What?
Appendages, they're not stuffed inside of the brain.
They're not stuffed. So the brain's a little bit of a black box, right? It's we've gotten it to tell us what's going on sometimes. In addition, can we do more experimentation here without violating human rights than we can here?
Yeah.
Yes, exactly. So I would even let you mess with my muscles and see how acetylcholine was released, because I would know that in all likelihood it wouldn't cause any body-wide impacts, right? However, dopamine, which is primarily but not exclusively a CNS neurotransmitter, is related to my feelings of reward and happiness. Would you volunteer for a study in which they see what happens to a human when I manipulate their levels of dopamine? No, I ain't volunteering, right, at all. And you wouldn't get approval, right? You wouldn't get funding or approval for that. But arguably, at least from my perspective, the CNS neurotransmitters are the truly interesting ones, right? They're the ones that we would love to get a grasp on. It's not as if we know nothing. We do know that a lot of it's not experimental in humans, and it's really hard for the rat to tell you exactly what his level of life satisfaction is, right? We can see how quickly he goes through the maze and how often he eats and has sex and all that kind of stuff and write it down. But we can't ask him whether he's got existential angst, right? I don't even know if they live long enough to get that, right? So the internal ones, a lot of times how we know the differences are when someone has a pathology and we can assess after the pathology the difference between my inherent level of dopamine and, for instance, somebody who has schizophrenia, right? It's really difficult to get a beat on how much dopamine, but what if you stained the dopamine or stained the receptors in the individual? Then you might see the difference between CNS dopamine levels in the prefrontal cortex of someone with schizophrenia and someone with normal dopamine levels. And you would say, oh, I see that one of the things that's going on there is that schizophrenia has absolutely high levels of dopamine release in the prefrontal cortex compared to somebody else. But that's kind of like, it's the accumulation of anecdotal evidence, because you can't do much experimentation with CNS neurotransmitter in humans. You can still get some ideas, but does that make sense to you guys? So we'll talk a lot about those. Okay, so, and then the last one is paracrine and its buddy autocrine. So we can do these at the same time. And paracrine and autocrine agents are really communicating usually within a tissue. So if I made this group of women right here, all cells in the same tissue, and something happened to you, like you got influenza B, and you needed to tell your other respiratory cells that influenza B was around, do I need to immediately call in the troops, or should I try it locally as well? Locally first? Locally. So what I would need to do is I would need to release a chemical that communicated with my neighbors. That's paracrine. And so do you think paracrine is generally used in intrinsic communication or extrinsic? Intrinsic, yes. Okay. How about quantities of chemicals to be released? Do you need to immediately go with high levels of paracrine, usually low levels of paracrine? And do you think that it's very likely to produce body-wide impacts? No. It's usually relatively local. There are situations in which it can become body-wide, and we'll talk about those in just a minute. But so it's basically local. So you're trying to do something local. Paracrine, a good way to think about paracrines generally are responses to injuries or infections, right? You don't need those immediately to tell everyone in the body. You can try to handle it first at home. Does that make sense? So, but if these guys are all respiratory epithelial cells, for instance, right? Would it make sense that if you have a receptor, she probably has the same receptor if you're identical types of cells? So in the rare instance in which you release it and it binds back to you, then it's behaving as an autocrine, right? Auto is in self. But autocrines are really just kind of a subcategory of paracrines. Like, it's like I released it to bond to my neighbors, but I'm the same type of cell as my neighbor, so it bonded to me and caused a response. Okay, paracrine / autocrine. Okay, so with generally speaking, this is going to be local communication, shorter distance, fast response, but not very broad. Usually, people by the time they take physiology know hormones generally, and they know neurotransmitters. But I don't think I learned about paracrine agents at all until I took physiology, right? I didn't know, even if I had met the chemicals, I didn't know like what category they fit into. So this is communicating with neighbors. And most tissues in the body have the ability to release paracrine agents. And the paracrines are usually kind of specific to that tissue. Go ahead.
Well, I was just going to say, because I'm so confused on the difference of neurotransmitters and the paracrine agents, because aren't they both like releasing next to each other?
They are, but what is the difference? Help him. Anybody, what's the difference between this one and this one?
One's a neuron.
Yes.
So it's basically neurons. It's just neurons.
It must be neurons that release neurotransmitters. That's actually a good question, though. They are both communicating very, very, like, next to the receptor. But is that one necessarily a neighbor? No, because the axons can be up to 1 meter long, right? So even though it looks counterintuitive, this can be long-distance communication, can't it? But paracrine, is it ever long-distance communication? No, it's communicating with the neighbor. Does that make sense? So that's actually a good question. You need that clarification. Again, in order to be a neurotransmitter, you have to have 2 criteria. You have to be a neuron, yeah, releasing it, and it has to be released right next to the receptor. Here? No, neither of these are in the bloodstream. Good clarification, right? Neither of these, by definition, are in the bloodstream, at least initially. We'll see the paracrines can get picked up by the bloodstream when you release enough of them. But released by a neuron right next to the receptor. Released by a neuron right next to the receptor.
But it's the
Good.
idea that the receptor can be 1 meter away.
Yeah, the receptor can be 1 meter away, right? So it can be, I mean, it's short distance communication if it's released between 2 neurons in my cortex, right? But it's not limited to short distance communication. It can be long distance communication if it's communicating between the cell body that's up here in the lumbar region of my spinal cord and the muscle cell that's down there in my little toe, right? So neurotransmitter or synaptic communication can be any distance communication. Hormones are usually long distance communication. Paracrines are generally short distance communication, right? And this is variable. Good? Okay. And by the way, long distance versus short distance, that's really just like a synopsis of all of it, because, I mean, the testes release testosterone that communicates to the brain, and we can say, okay, that's long distance communication. But they release testosterone that also communicates to the testes, right? So what makes it a hormone? Bloodstream, exactly, goes into the bloodstream, right? So the long distance versus short distance is shorthand for the true physiology. And the true physiology is how do you travel, so that you can figure out whether you can go long distances or short distances or something in between. Is that okay with you guys? Okay, so now, paracrine agents, again, are generally trying to accomplish short distance communication. So if we do this again and you guys are all, and you're communicating with one another and you say, hey, influenza B virus is around, tell my neighbors, right? And you tell them and they respond to it. But if you release enough of any chemical, it will get picked up by the bloodstream. So if, for instance, let's start with like an acute infection. I like had a damage and got acute infection into the skin, right? I would initially release paracrine agents that bring stuff to the skin, start an immune response. We'll talk about the specific ones in just a second. But can what starts out local end up causing body-wide responses like fever and sedation? Yes. If you continue to release it. For instance, I had this pathogenic infection. I actually released some paracrine agents, but there were so many pathogens that I still really needed to release more paracrine agents. Then what would happen is you release so many that they get picked up by the bloodstream. That is not hormonal. It is second-tier paracrine. It's the same chemical. Why did it get picked up by the bloodstream? Because you kept going at it. Was the bloodstream plan A? No, it was plan B, right? So if you release enough of the paracrine agent, it will get picked up by the bloodstream and can cause body-wide impact. So you can, for instance, start out with a wound that's local, end up with a fever, right? Start out with respiratory irritation, end up with fever and sedation. Yeah? Okay, so we'll talk about examples of that in just a second. Okay, so it still is paracrine. Go ahead.
So if that happened, would it become extrinsic?
It does become extrinsic, although they usually don't recategorize it. They just say that this is a second-tier paracrine response because the first tier was inadequate. So let me give you some examples so you'll actually know about how this works. Okay, so I never learned about paracrine chemicals until phys, by the way, even though I'd run into them before. But we need to figure out which ones are categorized as paracrine chemicals. There are tons and tons of different paracrine chemicals. There are at least 16 different categories of like one of them, and then there's a whole bunch of other categories as well. So no, you don't have to memorize them. You just do not have to know a little bit of the subcategories. So many different types of paracrine chemicals. Growth factors that tell your neighbors that you need to do cell division and protein synthesis. Does that seem like a paracrine activity? Growth, right, in an individual tissue. Cell division in an individual tissue. Do you need to tell the nervous system or the endocrine system immediately for that to occur? No. So tissue growth, cell division, growth factors, right? That's paracrine. So the way you think about whether it should be paracrine is, do I need the whole body involved in it? If I don't, I can do it far more efficiently by just releasing paracrine chemicals to my neighbors. How about blood clotting? Do I want blood clotting to be body-wide, or do I want it to be local to the wound? Definitely local to the wound. Because you're going to have bigger problems than bleeding if you clot your entire bloodstream, right? So that's local as well. Good? Okay. And then another example, which we run into, is histamines. Okay. So you guys have run into histamines before because you've taken antihistamines before. So what histamines are paracrine chemicals, and they're released primarily by basophils. Do you remember learning never let monkeys eat bananas? Basophils are the least abundant type of white blood cells. They are involved what?
What was the monkey thing?
Oh, that's the order of the abundance of white blood cells. Neutrophils, lymphocytes, monocytes, eosinophils, basophils. So I'm not a person for mnemonics, but that one always stuck with me. I don't know why. And I told this to my son last night, or yesterday, and there's a new anime on that is a Japanese anime made of the immune system functionality. It's fantastic. It's so good. It's called Cells at Work, and it's on Netflix. And so we've been watching it, and he's been learning about all the immune system. So I told him never let monkeys eat bananas when they were talking about basophils. And he's like, what's the basophil doing? Like, she's getting all wound up, and there's nothing actually there. I'm like, oh, that's an allergic response. And they're all characters. It's great. You should totally watch it, especially if you're taking your took micro, right? Really like. So anyway, that's the basophils. Basophils release histamines that are usually involved in allergic responses. They do other things as well. And histamines do, like if I have a respiratory irritant, I like snorted up some pine pollen and I'm allergic to it. What histamines can do is increase secretion in the nasal membranes and sort of make the nasal membranes close so that the respiratory irritants don't get in. So those are released by basophils and mast cells during an allergic response. And the reason that you use an antihistamine is because what an antihistamine does is blocks the target cell from responding to histamines. Yeah? That's how it works. Okay. You find an antihistamine that's specific to that receptor and that target cell, and it blocks it, so you won't have those responses. Go ahead.
So, okay, I just want to go back to it. So, I'm understanding that the paracrine agent, so for example, ibuprofen, it does the clotting agent, right? And it's not like sealing, so it becomes infected, and then that's when the secondary effects come in. Where
Yeah, I'm about to explain some of the secondary effects to you. Give me just a second, and I'll give you guys an example of secondary effects. Okay, so we've got histamines, we've got growth factors and clotting factors, and now we're going to start to get to what Maria was asking about. Okay, so another type of paracrine agent is called a cytokine. There's tons and tons of research going on into cytokines. They're really, really, really important in immune functionality. And so I'm going to oversimplify. You know how complicated the immune system is, right? It's like you could do an entire PhD just learning like how the immune system actually functions. So of course this is all an oversimplification, but it's enough to get us going. So what do cytokines do? Think of them as chemicals that are released usually by white blood cells, usually, not always, but usually by white blood cells. And they are part of the body's acute immune response to a pathogen. Okay? So white blood cell, of course, is going to be involved in immune responses to pathogens. They are going to release chemicals, and these chemicals actually are going to do sort of a bunch of necessary things, depending on which cytokine. Let me give you some examples. They could increase blood flow to an area. That would be good, right? Okay. They could activate another white blood cell. Yeah? They could cause inflammation, right? Inflammation sounds like it's negative, but it's actually the first step to healing. Right? It can have negatives associated with it, but it's the first step to healing. So they're the part of the body's acute immune response, usually released by white blood cells. Now, conceptually, do you need that to go body-wide first? No. But what if that failed? You would continue to release it, yes, until you ended up getting a body-wide response of fever. Yeah? If you release enough of those, you can get fever. You can get sedation. You can get those body-wide responses, which is, sedation is, you need to sit down because we are using all of your energy for this immune response, right? Okay, go to sleep. Let me handle that. I'll get back to you later, okay? And fever is, I can't take this out. Let's try increasing the temperature, right? Does that make sense? So they start out local, and they can and often do. These are among the paracrine agents that are really, really likely to have that second tier response, right? If it doesn't work the first tier, okay? And by the way, it's not like thinking about whether it worked. It's just the pathogen's still there. Still living pathogen, release more. Still living pathogen, release more. Still living pathogen, release more. Oh, I released so much that I actually told the immune system that we needed a fever, okay? So I still considered a paracrine. Okay, and then the next category is the ones we're going to take a minute to talk about, because you mess with these. So everybody messes with their paracrine agents. Some of us take things that mess with their neurotransmitters, and some of us take things that mess with our hormones, like for instance birth control pills or something. But almost everybody has messed with this category. So this category of paracrine agents are called eicosanoids. Can you please say that? Okay, the only reason I do that every once in a while is because it makes it more likely that you can spell it. And some of us are auditory learners, and you can also remember having said it. So, eicosanoids. So, eicosanoids are a huge category of paracrine agent. There's really, really varied. This is the one that has at least 16 different subcategories. Don't worry, I'm not going to make you learn them. But the reason that you are going to learn about these is because damn near every cell in your body makes them. Here are the 4 categories that you're going to learn of eicosanoids, and they are all derived from membrane phospholipids. So question for you, how many cells in your body have phospholipids in their membrane? Every damn one of them. Yes? And so you can make eicosanoids in damn near every cell in your body. They may be like specific to that cell and those tissues. So these are really, really ubiquitous in the body, and they can do all kinds of things depending on where they're released. So depending on which prostaglandin is released in which part of the body, they might cause an increase or decrease in local blood pressure and blood flow, like causing vasoconstriction and vasodilation. They can do that, right? They may, for instance, decrease gastric secretion or increase gastric secretion. So for instance, when the stomach is empty, the epithelial cells lining the stomach will release a paracrine agent that tells their neighbors not to secrete gastric secretions, right? Right? And why do they tell their neighbors? Well, because the ones at the bottom say there is nothing in here, and tell the ones at the top that they can save their breath, right? They can enhance the inflammatory response, so they can help the cytokines with inflammation. And again, inflammation is both the first step of healing and also something that we treat, right? Because it's uncomfortable and potentially painful, right? They can, if released in the respiratory system, dilate the bronchioles or constrict the bronchioles, constrict upon irritation, dilate if they don't have enough oxygen coming in. They can contract or relax smooth muscle. They can shrink the nasal membranes. And then the last two are those second-tier responses. Eicosanoids can also cause fever and sedation when secreted in large enough quantities to get picked up by the bloodstream, okay? So these are famous for doing that, causing fever and sedation. So the reason that these are worth talking about is because A, you are a human and you have a body, and this class, to me, is the user's manual that I wish that I had had when I was a teenager, so that I would know why I wasn't supposed to do certain things, right? Or should do certain things. But in addition, you guys are going to be caring for humans. And quite often those people will be in pain or have fevers. So let's talk about how this is related to pain relievers, anti-inflammatory, antipyrogenics, which are fever reducers, and all of those drugs, how they're related to these eicosanoids. So what we're going to talk about is two categories of drugs. The first category includes aspirin and the non-steroidal anti-inflammatory drugs called NSAIDs. And that includes, just for your mind, ibuprofen and naproxen sodium and some others. Acetaminophen is not included in this little story because it's a little different than the other ones. It's closely related, but not exactly. So aspirin and non-steroidal anti-inflammatory drugs. And then we'll talk about corticosteroids like prednisone, okay? So those are things you are going to or have interacted with, of course. So let's talk about what they have to do with this story. So aspirin and NSAIDs. So when we are taking aspirin and NSAIDs, we are taking them usually for pain, which is quite often but not always related to inflammation, right? We might be taking them for fever reduction, okay? And anti-inflammatories, right? That's kind of the reasons that you usually take those. There's another reason as well we'll talk about in just a second. So what do they do and how do they do it? Well, this is the membrane phospholipid, and these are the 4 eicosanoids that we're talking about. What aspirin and NSAIDs do is inhibit this part of the pathway, okay? And that part of the pathway is responsible for making these guys. So let's talk about the 4, okay? So let's meet these 4. Okay, so the prostaglandins are that big category that is responsible for inflammation and a whole bunch of different things, could be responsible for pain. These 2 right here, prostacyclins and thromboxanes, they're kind of telling you what they do with the prefix thrombo. What do you think those have to do with? Blood clotting, exactly. So what you do when you take aspirin or ibuprofen, less so with naproxen sodium, is you inhibit both the prostaglandins that could be causing inflammation, pain, swelling, fever, yeah? And then you have this unintended side effect of also blocking blood clotting. Does that make sense to you? Okay, so based on that, you've probably experienced a little bit of these cautions or a little bit of things that people might do for treatment. So my father-in-law has a heart valve replacement, and he also has hypertension. And so he is on anticoagulants. They call them blood thinners, right? And so he has to not also take over-the-counter aspirin or ibuprofen. Does that make sense to you guys? Because what he is going to do is inadvertently thin his blood even further, right? Which will lead to bruising and potentially bleeding out if he's ever damaged. Does that make sense? So you can't sort of combine those impacts, okay? I, on the other hand, have atrial fibrillation, which predisposes you to inappropriate clotting, and I have a valve defect. And so I'm not on any anticoagulants, but they would like for me to take, and I never do, I should, 80 milligrams of aspirin per day. But not because I'm in pain or have any swelling, but because it is actually doing what? Yeah, it's actually blocking those two coagulants. Does that make sense? Okay. So the unintended side effect of, for instance, taking, have you guys ever experienced this? If you take ibuprofen really regularly or aspirin really regularly, or when I do what I'm supposed to and take 80 milligrams of aspirin per day, yes, I have a decrease of inappropriate clotting, but also every time I run into anything, I get, instead of a bruise that big, I get one this big. Does that make sense? Okay, so we mess with these all the time, and we can mess with them with over-the-counter medications, but sometimes over-the-counter medications are not adequate, and you need a prescription medication called a COX-2 inhibitor, and they inhibit a specific form of cyclooxygenase, COX, right, cyclooxygenase, and they're way, way more effective anti-inflammatory drugs, and they are used to treat chronic inflammatory conditions that are not life-threatening. Like, for instance, you can take them for arthritis, you can take them for other inflammatory conditions. Does that make sense? Okay. Vioxx and Celebrex, have you ever heard those? Yeah, they're sold prescription. They got a lot of press a few, maybe 10 years ago, I can't remember, because when they first started being used, they weren't specific to the population, and there were some deaths. I think they were associated with Vioxx and lawsuits associated with Vioxx. It's still on the market. It's just that its target population is narrowed to exclude this subgroup of people that can't take it. So those are COX-2 inhibitors, and there's a little text box in your textbook for those of you who have the textbook that talks about the development from aspirin to COX-2 inhibitors. Go ahead.
I just want to make sure I was right. So the pathway we can block with the prescription, and then the little subcategory.
No, we block this with over-the-counter medications. Aspirin and NSAIDs. Those are COX inhibitors, but COX-2 inhibitors are better, they're targeted, and they are more effective. Okay. Yes, right? They also are more risky because there's certain populations that they can't be used in. So they're not sold over the counter. Go ahead.
So these, like ibuprofen and all that,
Mm-hmm.
block, like, obviously, all those,
Uh-huh.
I don't know how to say those words.
Prostaglandins, prostacyclins, and thromboxanes.
But you'll also be bruising and your blood won't clot.
If you take them really, really regularly, right? If you are an everyday 400 milligram ibuprofen person, you are probably going to bruise more than the person who takes it just every once in a while, every 2 weeks. I'm not saying that you are necessarily causing anything life-threatening, but you will have an impact with chronically suppressing these clotting factors. Is that okay?
So we would use the word inhibit.
Yeah, you are inhibiting. You're inhibiting the production by blocking this enzyme right here, cyclooxygenase. Good? Okay. All right. But now let's talk about what you do in situations in which the inflammation is either life-threatening or the inflammation is the problem. Okay. And you can't manage it by other mechanisms, so you have to really, really use a medication that is going to have benefits, but also some massive side effects. And we'll talk about why the side effects are massive. And this is the category of drugs that are the most powerful anti-inflammatory drugs that we have, but you do not take them lightly, and they are all prescription medications. And these are called the corticosteroids or adrenal corticoids, and prednisone is an example of one of them. Do you guys know of any of these? They typically just call them anti-inflammatory steroids, but there's a whole bunch of different brand names. And these are big gun steroids, big gun anti-inflammatories. And the reason that they are so effective is that they block right here. They block phospholipase A2. So you have these that are involved in the inflammatory response. You have these that are involved in the inflammatory response, but then you take out all of these incidentally. You didn't really mean to. It's not what you were trying to treat. It's just what you end up doing. So you block phospholipase A2. And these corticosteroids are really effective anti-inflammatories. But why the hell would you take them? I'll tell you why they have so many side effects. They have massive amounts of side effects later. Well, what if I had a closed head wound? If I have a closed head wound, the inflammation is the life-threatening thing. Do you see? So take something that takes out the inflammatory response regardless of the costs. Or what if I have rheumatoid arthritis? Rheumatoid arthritis is debilitating. The inflammatory response in rheumatoid arthritis is such that you cannot actually live your life, right? So you have to treat the inflammation. Or what if I had a child with asthma that was severe enough that the bronchodilator puffer that you use was not adequate, right? So the bronchodilator is just treating the paracrine chemicals. It just actually sort of blocks, and then you have bronchodilation. So that's all well and good. But if that doesn't work, then you can also get a steroid inhaler. And a steroid inhaler treats the inflammatory condition in the airway. And interestingly, you can't stay on the steroid inhaler for very long. So even if your kid had life-threatening asthma and you tried to treat it with a bronchodilator, you tried to do all of the other things, they can give your kid a steroid inhaler and they only give them the prescription for like a couple months and then they have to go back off of it. And parents have a really, really hard time understanding why the hell you would take them off something that works. But let me tell you guys why. Because, and this is hard to grasp, and it's okay because we'll reinforce it when we get to the endocrine system. But the medication that you use to block all of these paracrine agents, listen carefully, the medication that you use to block this is a hormone mimic. And it mimics the hormone cortisol. That's why they're called corticosteroids, right? Okay, and cortisol is a really, really effective anti-inflammatory, okay? But it doesn't just have receptors there. It has receptors all over the damn place. So when you are on, for instance, prednisone, have you ever known anybody or ever been on prednisone for any length of time, any corticosteroid? You get all of these secondary impacts, and the secondary impacts include weight gain, because cortisol is actually a metabolic hormone. They include water retention, because cortisol impacts your kidney function. They include the brain impacts, because cortisol is lipid soluble, goes straight through the blood-brain barrier and impacts the brain. And cortisol in large quantities, you do not want to depress the inflammatory response such that you shut off the immune system. Cortisol in large quantities will completely depress your immune system, which makes you, of course, wonder, why the hell would you use it? Because it is the most effective anti-inflammatory that we've ever found. And again, sometimes the inflammation is the problem, right? And so you're willing to make this little devil's bargain that says, I'm going to take care of the problem, and I'm going to give you a whole suite of other ones, but you're not going to die of the problem, right? So you have to be really careful about dosing because you can have downregulation with the hormone receptors. You have to be really careful about being intermittent and using it and going off, right? But then, of course, your inflammatory condition is going to come right back and you're probably going to have to go right back on it. So this is sort of a hole in our medical care that this is the most powerful anti-inflammatory that we have. If we could find something that blocked this pathway but wasn't a hormone mimic, it would be a freaking medical win, and we don't have it yet. Go ahead.
So my cousin has Crohn's disease.
Yeah.
Is an inflammatory bowel
Yes.
disease.
Mm-hmm.
And when she first was diagnosed, it was bad enough that they put her on prednisone for
Yes.
a while, and all of that happened. But now they tell her not to take like ibuprofen and aspirin. She's only supposed to take Tylenol. Why would they if like that helps the inflammation?
I don't actually know, but I suspect that they're worried about the side effect that those are really irritating to the gut epithelium. Aspirin and ibuprofen are really irritating to the gut epithelium. I don't know if that's why they caution her against it, but that's what I would think. There may be, and Tylenol is not irritating to the gut epithelium. In addition, those are detoxified through your kidney. Prednisone can cause kidney damage, and acetaminophen is detoxified through your liver. So could be those. But I mean, it's not a thing that I know. Go ahead, Paul.
Cortisol is produced naturally, isn't it? Is it stress?
Absolutely.
Why would you have like an anti-inflammatory response to stress?
It is such, oh, okay, so cortisol, the why I actually don't know. The cortisol has entirely different impacts on the human physiology in normal homeostatic levels and in high levels. So in normal homeostatic levels, it is not an immunosuppressant. In higher than normal levels, or when chronically secreted, like with chronic stress, it depresses the immune system and depresses the inflammatory response. So I think what you're seeing here is it is eventually depressing the immune system. The perspective that I use to teach it when we get to the endocrine system, and this is the most complicated hormone that we have, is that when you are under some kind of acute stress, you would like to suppress any functionality that would not be helpful with that acute stress. And immune is long-term functionality. It's like hopeful. And when you secrete chronically high levels of cortisol, you have said, I don't know if there's going to be a tomorrow, so let's not spend any money on tomorrow, right? And it's really massive in large quantities. In small quantities, it doesn't have an immunosuppressant effect. So we will talk about cortisol in enough detail that you will think you've got it and then become confused again, because it's taken me 10 years to even figure out how to teach cortisol. But I try to do a better job every year, and I try to read the literature about it. It is the hormone that has the most broad effects in the body. And of course, we have to deal with it because it's both a metabolic hormone and a hormone that's related to stress. And you release higher levels of cortisol when you're under stress. But we will talk about that. I'm not sure that I will be able to answer your question, but I will be able to clarify it so that you'll continue to look for it. Okay, so your corticosteroids. So again, just to reiterate, and I'm not going to test you over their functionality yet. I just want you to understand the basics is that they inhibit this. But then the unintended side effect is that by inhibiting that, you're also screwing up your hormone system. You're actually screwing up your inflammatory condition, and you can depress your immune system. Okay, so those are adrenal steroids or corticosteroids. And then autocrine agents, we already did. Autocrine, we said, was just when the paracrine actually incidentally talks to itself, right? Because it's got the same receptor, right? That's just autocrine. Okay, now, are there any situations in which two cells can communicate with one another without releasing anything into the extracellular fluid? Yeah, because you learned about them in anatomy. If the two cells are neighbors and they both have gap junctions stuck together, then they can communicate without going into the extracellular fluid. Is that okay? Okay, so this is, of course, instantaneous, and you don't need very much of the chemical to do it. But doesn't it mean that cell 1 and cell 2 also have to behave the same? Right? They have to be doing the same thing, so it's kind of a one-trick pony, right? And also it means that you can't, for instance, use gap junctions to communicate between a cell in the little toe and a cell in the brain because they're not next to one another. So, but the cells do tend to behave as a big unit, right? And of course, like in cardiac muscle, right? If this one contracts, then that one's going to contract next if it's going that direction, okay? So they call these gap junctions everywhere else. For some reason in physiology, they made up a word for it. You know that looks like a made-up word. They call it a connexon. It's a gap junction, people. It's a gap junction. So that's a gap junction. They're relatively rare in the human body. They do, of course, exist in cardiac muscle and smooth muscle and the respiratory epithelium. Interestingly, during embryonic development, before your brain develops the ability to release neurotransmitters, when you're putting together like the scaffolding of how the neurons are going to be connected, they're all connected by gap junctions. And then as the brain matures, they pull apart so that they can release neurotransmitters. Because if they were still all connected with gap junctions, all of your neurons would be on or off at the same time. And that sounds like a level of crazy that even I have never experienced, right? Do you want all your neurons on? No, I'm trying to shut up the ones that are embarrassed about something that happened in 7th grade. They still talk to me every damn day, and I don't even know anybody from 7th grade. Why the hell do they care? I'm like, shut up, turn off. They won't. So now, this sounds like I'm going to try to trick you, but I'm not. So how do you, for instance, look at a neurotransmitter that you may have not met before and figure out whether it's a neurotransmitter or a hormone? Did I say neurotransmitter? Paracrine agent, and figure out how it's behaving. You look at it and you don't memorize that dopamine is a neurotransmitter. You look at how dopamine is behaving in that instance and say that dopamine is a neurotransmitter there. But your body and evolution is the original reduce, reuse, recycler. So don't be at all surprised that if you see dopamine released between two neurons, then it's behaving as a neurotransmitter. But your body already knows how to make it. So in a different place in the body, it might dump it into the bloodstream. And then it's behaving as a hormone. Or it might release it to communicate with another cell. And then it's behaving as a paracrine agent. So don't think that I'm going to try to trick you. I just want you to, for instance, instead of just memorizing dopamine is a neurotransmitter, put an asterisk on it in your brain that says, unless it's behaving as a different one, right? Because of course, dopamine is going to be a super important neurotransmitter, but we're going to see it doing other things in other places in the body as well. And cortisol is a super important hormone, but you might see it doing something else, right? Does that make sense? So you really have to look at what it's doing, right? Instead of just memorize what you think it's going to do. Okay, and then the last little tidbit, whenever you see these, I think I pointed it out to you, it's a rabbit hole, right? Because you can go down a rabbit hole with any of this stuff, and these are things that I think are interesting rabbit holes. I never test you over these unless I say, I'm going to write a bonus question about that one, right? But this is a TED Ed about why do we sweat. It doesn't sound very interesting, but it's all about homeostasis and negative feedback. And then that one's, are you a morning or evening person? So that's just if you're interested or want to deepen your knowledge, and they get more interesting, and sometimes there's journal articles as we go through. Okay, so with that in mind, we are ready to move to the next chapter, which is cell metabolism, which is, I admit, a lot of chemistry, but for those of you who are chemistry phobic, it's only chemistry as it applies to physiology. So it's applied chemistry. You're not going to be balancing equations and doing stoichiometry. You are going to be trying to figure out why the hell you care if carbon dioxide increases in concentration, what you would get out of breaking down a lipid, right? That makes sense? Okay. So if your brain always disengages with chemistry, try to keep it engaged, because I'm not going to teach you anything that is extra and not related to physiology, especially because I don't like teaching chemistry. If I could get away with not teaching it, I wouldn't, because I see you guys gloss over, right? I like teaching gee whiz physiology. It's more fun. Note, please, that if you know that your chemistry is a little weak, make sure that you do the before you begin section, right? And I have specific figure references for stuff. All right, so let's start with a big picture of what is metabolism. So the way that metabolism is talked about in like the popular press is the way metabolism is talked about is like, oh, that's the reason she can eat a burger and lose half a pound, and you can eat a burger and gain half a pound. But that's not what we're talking about metabolism. We're talking about more of a physiological perspective and a cellular perspective of metabolism. So what is metabolism at the cellular level? Well, it's really like the sum of all of the chemical reactions that go on inside of a cell. Both the chemical reactions that break down stuff and build up stuff, the ones that consume energy and the ones that release energy. So it's like the net effect of what's going on in the cell. So all of the biochemical reactions that occur in a cell, both the synthesis and the breakdown of organic molecules, okay? So before we get any further with metabolism, let's make sure that you guys are familiar and can actually use these words now. You've heard anabolism and catabolism before, right? And I always had trouble figuring out which one was which, but later on we will be talking about anabolic steroids and catabolic steroids, and it's difficult to make those terms meaningful if you don't remember what anabolism and catabolism is. So what anabolism is taking small, like organic molecules, they don't have to be organic, but organic molecules, and making something bigger with them. And generally speaking, anabolic reactions, what do you think, just conceptually? Release energy or require energy to take small things and make it into bigger things? Yeah, they require energy. A great example would be protein synthesis, right? You have amino acids and you want to make a big folded protein out of them. That's an anabolic reaction. With that in mind, you will be talking this semester about anabolic steroids. An anabolic steroid would be, what do you think? Testosterone or cortisol? Testosterone, right? And because what it does, and the reason that, for instance, people supplement it off-label, right, would be to build muscle mass, make more of you. Yes? Okay. And then catabolism is taking usually a large organic molecule and breaking it down to smaller things and releasing energy in the process. A great example of a catabolic reaction would be taking glucose, C6H12O6, breaking it down to CO2 and H2O and releasing energy. It's byproduct, right? That's a catabolic reaction. Okay. And we will learn about catabolic steroids this semester. And one of the other freaking side effects of cortisol, freaking cortisol, man, it's all up in everybody's business, is that it is a catabolic steroid. And when you take cortisol over long periods of time, it will actually break down your muscle mass, right? Catabolic steroid, cause you to lose muscle mass. And the pisser about that is that what does that do to your metabolism? It trashes your metabolism, exactly. Yeah, so that's anabolic and catabolic, and we'll learn those and use them this semester. Okay, and then just a few like terminology things so that we're on the same page about terminology, and then we'll get back to the physiology. Okay, so this week in lab, you're going to be doing metabolism, and you're going to be dealing with organic molecules and that kind of stuff. And one of the things that you're going to be doing is called hydrolysis. It's not hard though. Hydrolysis is, to oversimplify, when water reacts with a molecule and breaks the bond. So, an example, proteins, a big protein, would be hydrolyzed to amino acids in the process of digestion before you could absorb it, because you can't absorb a whole protein, but you can absorb amino acids. So what does that look like? This is just a simplified example. A is bonded to B. Look, use water, yeah, and you can break down and bond A to the hydroxyl ion and B to the hydrogen ion, right? And you've broken them down with water. That's hydrolysis. Everybody okay with that? Okay. All right. Phosphorylation and dephosphorylation. So I want you to imagine that inside the cell I have an enzyme, but I don't want it to be active all the time. I just want it to be able to turn it on and turn it off, right? So why wouldn't I just make it when I need it? Is making proteins super quick? No. So what I can do is I can have a mechanism of turning them on and off really quickly. Here's an example. I've got A, which is my enzyme, and I've got an inorganic phosphate. That's P sub I, right? If I phosphorylate it, let's say that turns it on, right? What's a quick way that I can turn it off? Dephosphorylate it, right? And you do these with kinases and proteases. You guys have learned those before. Kinases and phosphatases. Okay, now just conceptual question. What is the normal, the really common source of that inorganic phosphate? Where do I usually get it from and put it back on? What always has some phosphates hanging off of it? Yeah, ATP. You can use GTP. You can use other things. But ATP, you have a lot of it. You can borrow a phosphate and stick it back, right? You can also use ADP, right? Okay, so that's a common mechanism for turning enzymes on and off, and we're going to get to that today, maybe today. And then the dreaded oxidation reduction reactions, don't worry, I'm not going to make you do them, okay? I just want to make it so the words are things that you can use as we actually go through. So what is an oxidation reaction? This is way oversimplified, and if you're a chemist, just hold your breath until it's over, okay? Oxidation is oversimplified, removing electrons from an atom or molecule. Oxygen is usually involved in the process on this planet, okay? Reduction is accepting the electrons by another atom or molecule. So I've got oxygen here, and I'm going to take an electron, right, and I'm going to oxidize it, right, and then oxygen is actually going to be reduced. So oxygen is usually doing the removing and accepting. So why the hell do you care? You care because you can't in physiology get away from cellular respiration, and cellular respiration is a series of oxidation reactions. And do you ever remember hearing, although you hated it, that oxygen was the final electron acceptor? Yeah? Okay. So it's a series of oxidation reduction reactions. You are not going to be required to truly, truly understand them. Just use the words all semester long. Okay? All right. And then the last tidbit, and then we'll get back into the true physiology, is just the concept of a metabolic pathway. And the concept of a metabolic pathway just says that if I am trying to make an organic molecule in the cell, maybe a protein, maybe a lipid, is it generally going to be one single chemical reaction, or is it usually a series? of chemical reactions. So if, for instance, I have A and I want to make G, right? It's not one chemical reaction. A would dissociate to B plus C. B plus C would come back together and form D. D would dissociate to E plus F, and that would make G, right? So these are just fake. And one of the important things to understand is that in us, of course, these series of chemical reactions inside a biological organism are generally enzyme catalyzed. Otherwise, they wouldn't work quickly enough. So this would be catalyzed by enzyme number 1, yeah? This would be catalyzed by enzyme number 2, enzyme number 3, and enzyme number 4. Does that make sense? So a series of enzyme catalyzed chemical reactions is a really simple definition of biochemical pathway. I know you don't want to know, but I'll show you what a biochemical. So here's, ready? Don't worry. Don't drop the class. You don't have to memorize this. Here is the biochemical pathway for just glycolysis, right? Every single step right here, right, is going to have, wait, that one's, and here's Krebs cycle. Every single step is going to have an enzyme that catalyzes it, okay? You do not have to do that in this class when you take biochemistry. A lot of times you do, but not in this class. Okay, so keep the metabolic pathway in mind because we're going to refer back to it in just a few minutes. Okay, so now before we get into metabolic pathways, I want to focus on enzymes for just a second, and I want to look at enzymes from a physiological perspective. So what an enzyme is. So I always had trouble with the terminology that they use to describe enzyme function when I took chemistry. They always describe enzymes as lowering the activation energy for a chemical reaction or catalyzing a chemical reaction, and therefore increasing the rate of a chemical reaction. But I was really, really confused because they're actually using the term energy in two different ways. So for instance, they could say, oh, this is an exergonic reaction, meaning it releases energy, but I need an enzyme to catalyze it. I'm like, what the hell are you talking about? You literally just told me that it was an exergonic reaction, but I need an enzyme to lower the activation energy. I'm like, I'm going to memorize it. I have no idea what you're talking about. So my biochemistry professor taught enzymes from a different perspective, which really worked for me, and it stuck with me. And that is that enzymes are primarily related to increasing the statistical likelihood of a desired chemical reaction. So let me show you. That's just an example. It doesn't have to be related to that one, but A plus B, I want to go to C, right? This is the desired chemical reaction. And let's say A and B are substrates that are inside a cell, and I want C to occur. I could just wait for A and B to run into one another, and I would get some small level of C, right? Does that make sense? Okay, just statistically, right? But what if I made a meeting place for A and B that was shape specific and was attractive to both of them? Does that make sense? And this is enzyme number 1. You with me? Okay, so can you see that with that in mind, the desired product is going to occur more frequently? Yes? Okay, so that's what an enzyme is. An enzyme is a location that is attractive to the substrates that makes the product more statistically likely. Does that make sense? And so also that gives you some predictive capacity. It also tells you that if you understand it from this perspective, you can sort of predict how you can increase the concentration of C. So if I had 10,000 molecules of A and 10,000 molecules of B, but I only had 10 molecules of the enzyme, am I really going to get a massive increase in the amount of C? I'm not, right? Okay. Likewise, if I had a whole bunch of enzyme number 1, but very little substrate, I still wouldn't get an increase in the concentration, right? Or what if A fit really well, but B had a poor fit on the enzyme? Would I get much product accumulation? Right. So it's kind of based on statistics and prediction, right? And for me, that works, right? It's also true, right? It makes more sense and it's also true. So let's talk about what this allows you to sort of predict. Let's make sure that we sort of got the basics down first. So when you have any chemical reaction, the reactants and the products. You guys already know this. But when you have an enzyme catalyzed one, we call the reactants that fit in. These are called substrates. You know that, right? And what is this site right here where the substrates bind? Yeah, active site. And the active sites and the substrates shape specific. Change to shape, change functionality, right? Okay, so the substrate combines with the enzyme at the active site. Now, one of the important things to understand is that this means that really the enzyme is a location. It's not like directly involved in the match that you just made. So for instance, if the product that you want is a marriage, right? What you're going to do is go to the meeting place of perhaps church so that you can increase the likelihood of that product, right? But you can use that church over and over again to make that product, right? If the product that you wanted was a hookup, you don't go to church, do you? I mean, it could happen, right? But the statistical likelihood is less likely. You go to Tinder. And every once in a while, I'll bet you that Tinder produces a marriage, but it's statistically unlikely, right? Okay, so what happens is that you can actually reuse the enzyme, right? Think of enzymes as durable goods, like a washer and a dryer, not disposables, like a paper towel, right? So what you can do is the substrate has a shape, right? The product has a different shape. The product doesn't fit the active site, so it falls off. And then you can use the enzyme over again. Does that make sense? Okay? So you can use it over and over again. Now that does not mean that you never need to make enzyme again, because are you going to have to buy another washer in your lifetime? You absolutely are. But it means that you can use it until the damn thing wears out. So Ruby does not have the same iteration of enzymes that she had as an infant, but she has similar enzymes to the one that she had as an infant. So she'll replace them when they start to wear out. Does that make sense? So if her one enzyme was named Elsa, right? Elsa's long gone, she's history, right? But you have things that look and function just like Elsa later. Does that make sense? So you can reuse them, and they're actually not consumed or permanently changed in the process. Everybody okay with that? So not consumed or permanently changed in the process. So now this gets us to, if we can use this predictor, let's talk about a few things that can change potentially the rate of product accumulation, right? So that's a goal, right? And the first one is the concept of saturation. And I know you've met the concept of saturation before. Saturation in this context, and saturation can mean something else too, is really when the enzyme is full, it will limit your accumulation of product, right? So we've got the substrate concentration and the reaction rate. And the reaction rate could be indicated by how much product is accumulating, right? Does that make sense? Okay. So what will happen, and this comes back to the whole idea of, I can continue to add A and B as much as I want, infinitely, at least theoretically. But if I have X amount of C, right, it is going to limit the reaction rate. Does that make sense? So you can add more substrate if you want to, but if, for instance, I had 10,000 molecules of A and B and only 500 molecules of C, what's going to happen is the reaction rate is going to go up until what occurs with the enzyme? I know it's called saturation, but what's physically occurring with the enzyme? It's not equilibrium. What is physically occurring with the enzyme? Like what? They're full, right? The active sites are full. So what's happening to the A and B? They're just waiting in line, right? You can't go any faster when the enzyme is full. Does that make sense? So it's full, and you're waiting for it to fall off. And I don't care how many you have behind you, right? It's still full, right? What is the only way that you can change the saturation rate? Increasing the concentration of enzyme. Now, if I work in the lab, right, I can just do it by squirting it in there, right? You guys are going to do that this week. Squirt some enzymes in there. But in your body is making more enzyme instantaneous. It's not even always desirable, But sometimes, again, for instance, if your set point for enzyme was down here and your error signal was really big for a long period of time, you could say, oh, I need to up my set point for the enzyme, right? So for instance, when I moved from Texas to Utah, after a couple of weeks, I upped my set point for the enzymes involved in erythropoiesis, red blood cell synthesis, right? Okay, but not immediately. It doesn't happen instantaneously. In the lab, you can do it instantaneously. So the only way to increase your saturation rate is to increase the concentration of the enzyme, okay? So the other things that can impact whether you accumulate C or not is this concept. So this concept is called substrate specificity. So let me just give you a visual for it. So substrate specificity. So we have been told for ages that enzymes are very specific about the substrate that they will bind, and that's just truthy. It's not true. Okay, so you know that there are a lot of molecules that are shaped similarly to other molecules. So here's my favorite substrate. It will bind really well. By the way, this binding to the enzyme is loose and reversible. It's primarily hydrogen bonding, right? You bond and then you fall off, and you bond and you fall off. Okay, and this is my favorite substrate. And since it's my favorite substrate, does it bind more quickly or more slowly than other substrates? More quickly, right? And if it binds more quickly, I'm more likely to accumulate the product, right? Now, this one, in a pinch, might bind. Substrate A, right? Might bind, okay? But will it bind as quickly? And so what can you predict about the rate of chemical reaction? It's going to be slower, exactly. And then this one, never, ever, not under any circumstances is it welcome, right? I don't know, this one may be on a super duper cold day, right? So what you can say about the concept of substrate specificity is that some substrates will fit the active site of the enzyme better than others. And with greater substrate specificity, do you increase or decrease the chemical reaction rate? Greater substrate specificity, increases the rate of the chemical reaction. Does that make sense? Okay. Okay. So I'm going to say this a couple of times just to make sure that you get it. Substrate specificity implies multiple possible substrates. Does that make conceptual sense to you? Okay. All right. The other one is just really logical. What is the impact on substrate concentration and the chemical reaction rate? Is that as substrate concentration goes up, what tends to happen to the reaction rate? It goes up until what? Until you hit saturation. Yeah, until you hit saturation. Everybody good with that? Okay, so that one's pretty good. And then the last one we'll talk about today is the concept of enzyme substrate affinity. And you have to listen to this because it's similar to specificity but different. Okay, enzyme substrate affinity. And this has to do with more the enzyme than the substrate. So to make it make sense, let's hold our substrates constant and say we've got the ideal substrate, but my enzymes are different than his enzymes, right? Okay, so we're different individuals. We don't have identical forms of all enzymes. Enzymes are genetically determined. He is not my brother or my son, right? And he's not an identical twin. So we're going to have slightly different enzymes. If the enzymes are different, it can impact how well they bind to a given substrate. Holding the substrate constant, yes? Okay. This concept is called enzyme substrate affinity. And so it says that if my enzyme has a high affinity for the substrate, I'm going to have a really fast rate of chemical reaction all the way up to saturation, right? Okay. It means the enzyme fits the substrate really well, right? So again, I'm holding the substrate constant this time and varying the enzyme, okay? If, however, his metabolic enzyme does not fit the given substrate very well, can you see that it's going to be a slower chemical reaction rate, slower to get to saturation? Yeah? Okay. Okay. So what is the difference between substrate specificity and enzyme substrate affinity? Listen. Substrate specificity implies multiple possible substrates. You with me? But enzyme substrate affinity implies multiple possible what? Enzymes. Yes. Could both of them happen at the same time? Yes. But that makes it confusing as hell. So we have to separate them first, right? And do I, quite often, have two forms of an enzyme in me because I've got two parents? Yeah, I have two forms of a lot of enzymes, but between two individuals, we are going to have some variability in our enzymes, right? Okay. So this has to do with the fact that not all enzymes are shaped exactly the same as all other enzymes, even if they were supposed to be. Because of course genetic variability varies the shape of proteins. Is that okay? Okay, and we will stop there for today, and I will see you guys on Wednesday. Please finish your quiz.